Good afternoon, everyone, and welcome to Automation Alley's virtual tech takeover this afternoon, hosted by Phoenix Contact. My name is Allison Trumbull. I am Automation Alley's Technology Relationship Manager. Here at Automation Alley, we are Michigan's Industry 4.0 Knowledge Center and a World Economic Forum Advanced Manufacturing Hub, or AmHub. We obsess over disruptive technologies like blockchain, 3D printing, and AI. Our goal is to take these really big, complex concepts and make them easier for companies and individuals to understand and implement. So we work with a wide range of companies, from those that are really just starting to grasp the concept of software first mindset to thought leaders and innovators in Industry 4.0. And we do this by hosting a plethora of events, such as today, and obtaining content from every aspect of Industry 4.0, academics, and we really want to give businesses a competitive advantage and help them along their digital transformation journey. So speaking of events, I do have updated news on our Integrate or Industry 4.0 conference. It's now going to be May 10th of 2022, and it's going to be at the Suburban Showplace. If you have any questions, let me know. There are sponsorship opportunities as well. Also, if you are a Michigan manufacturer, you do receive one free ticket to that event. So please reach out if you have any questions. As well, we do have our Global Economic Outlook coming up in January. That will be a hybrid event, so in person and online at the Townsend Hotel in Birmingham. So again, if you have any questions about participating, speaking, sponsoring, or attending, please reach out, and you can also find all of this information on our website. But on to our presenting company this morning. Phoenix Contact is a manufacturer of electrical control products used to help automate production processes all around the world. With over 100 years of implementing factory automation solutions across a range of industries. Their privately held, vertically integrated company has over 30,000 factory automation products, which are found with control cabinets around the world. Phoenix Contact has the engineering expertise to help customers rescue data stranded on the factory floor and deliver it to the highest level systems for analysis. Today, we're going to be discussing 4 simple steps to building your digital factory now. Starting down the path of digital transformation within your organization can feel complex, intimidating, and expensive. This discussion is really going to help demystify the topic by breaking down the implementation into 4 simple steps. We'll use real-world use cases from both customers and Phoenix Contact's own factories, in which they've already implemented digital factory solutions. So this morning, I'm going to be joined by Mike Brooks, who is the Vertical Market Manager for Factory Automation. Mike has been with Phoenix Contacts for over 40 years and has experience helping end users, machine builders, and system integrators solve their automation challenges. The topic of Industry 4.0 and IoT is a personal passion, with the goal of helping to simplify complex subjects so that customers can begin the journey and start to realize the benefits of digitization. So again, thank you everybody for joining today. We will have the chat option available. So if you have questions, please throughout the presentations, feel free to type them into the chat. We'll have a couple of Q&As will go back and forth as well. If you have any questions, feel free to reach out to us. So again, thank you for joining us. And Mike, the floor is yours.
Well, thank you very much, Allison. And it's a pleasure to be with you and the folks here within Automation Alley and all of the viewing audience today. So again, thank you. As Allison mentioned, I've been at Phoenix for about 10 years, but involved in factory automation for about 40 years now, starting off on the plant floor as an electrician and working my way up into various departments and things like that. But the topic of Industry 4.0, I first started to see it come about maybe about 7 years ago. And at the time, I really didn't understand what it was. And I started, I guess, just investigating it, researching it, studying it. And in around 2017, I said, let's do a survey to customers to see what it really means. In 2017, the response in general was not so positive. It was mostly, we feel like it's a rebranding of what you already have. you're calling your industrial switch an IIoT device and things like that. So I thought, okay, well, what is it that makes it so complex? So that's where I personally started down this journey of trying to take some of the mystification out of it, try to make it a little bit more simple. And working with our team in Germany, we've now helped to develop at least a very, I would say, hopefully simple approach that's got substance to it around the topic of Industry 4.0 and digitalization. So with that, I'd like to get started, and I'll share with you my presentation here. So Allison, could you tell me, can you see that?
Yep, if you just want to put it in presenter mode, you'll be all set.
Yep, thank you.
Perfect.
All right, thank you very much. So for today, I'd like to first give you just a brief, Allison gave you a little introduction to Phoenix Contact to take that just a little bit further, and then get into the substance here, and that are the basic steps to help achieve digital factory. We've broken that down into 4 basic steps to achieve that. For each of those steps, we're going to talk about some of the terms. Now, the terms that I'll share with you, or the definitions, are not the Webster's or Wikipedia. These are the Mike Brooks definitions, so they may be subject to some scrutiny, but I try to make things as simple as I can because I'm a simple person myself. I'll also talk about the things that need to be considered at each one of these steps. Having based on the experience that we've had over the last 4 or 5 years of helping customers implement this, we find very consistently here are the steps that are taken that, or at least should be considered as you're approaching this topic yourself. And then we'll illustrate that through various use cases and examples that we've done with different customers in implementing these strategies. And in the final, we'll recap and then provide you some resources from Phoenix that will allow you to come back to this subject matter if you want, or look up and further investigate it. So with that, I'd like to share with you a little video about Phoenix Contact.
One thing that has remained unchanged at Phoenix Contact since 1923 is our passion for technology. With new ideas, we turn challenges into opportunities.
Sorry about that.
And into solutions for the future. Phoenix Contact is a German family-owned company and global player. Thanks to our several development sites, 10 production sites, and more than 50 worldwide sales subsidiaries, our solutions are always where our customers need them. The world is becoming more intelligent, more flexible, more digital. Today already, we're developing appropriate products and solutions. For example, web technologies and security mechanisms are already part and parcel of many of our products and manufacturing processes. Together with our customers and partners, we are helping to shape Industry 4.0, the intelligent production of tomorrow. Keeping in mind the sustainable use of resources and respecting the environment are priorities for us. Let's look ahead and shape the future together.
So a couple of the things that make Phoenix unique is that, and one of the biggest things is the fact we're still a privately held company. It's owned by a family in Blomberg, Germany. They started the company back in 1923, so we're approaching 100 years of serving customers around the world. The picture you see there is actually our headquarters in Blomberg, which literally the company is the town. Nearby in Bad Pyrmont, Germany, we have another headquarters or group, which is our electronics group. And then we also have manufacturing, distribution, and logistics in Nanjing, China, which serves the Asian part of the world. And then here in North America, our headquarters with logistics, engineering, and sales is in Harrisburg, Pennsylvania. So we serve the Americas out of Harrisburg. So the company is very vertically integrated as a company. What that means is, much like the Henry Ford model originally, we have plastic that comes in and copper and raw materials, and we have parts that go out, and we own the manufacturing process from end to end. And in doing so, we really feel we can help other manufacturers based on our own manufacturing expertise. We're so proficient in manufacturing, we manufacture a lot of our competitors' products as well. So not only do we make stuff with the Phoenix Contact brand, but we also make things for others. Our product portfolio has grown. The company started back in 1923 by inventing the modular terminal block, and a very simple product in which you connect wires, and they made it in a way that you could expand it modularly. But over the years, we've grown tremendously in terms of our product portfolio into anything with connectivity, industrial automation products, anything that goes in a control cabinet, you would find a Phoenix product behind some control cabinet. So with that, I'd like to talk a little bit about the digital factory. Digital factory is a Phoenix kind of brand term, if you will, related to the subject matter of Industry 4.0, IIoT, call it what you will. But what our approach is, as I mentioned, it was started by our colleagues in Germany. And they said, let's take the topic and let's make it simplified by developing 4 steps to helping customers achieve that. And for each of these steps, let's work on developing I would consider, they call it generic digital architecture, or what I would call it a 80% done solution. So something that you could take off the shelf that would be applied to the application, that's about 80% done, with the last 20% being the part that you need to use or to customize based on your specific needs and applications. So doesn't require a ground up effort to do it. The other, for each of the topics, we also decide to put together training materials. So there's very comprehensive training available for each one of the topics that we're going to talk about today. And there's both a beginning and more advanced type of training available. And this is available to anybody in the community. And we also then stood up a shop, if you will, an open source shop. Our core philosophy is in non-proprietary open source application-based solutions. So most of the market is very proprietary in terms of how you get a solution. It is that manufacturer end to end, kind of take it or leave it. Ours is, we have parts and pieces, we have things that go together and things that talk together with others. And so we've proven those solutions internally. And that's the last part of the function of Digital Factory, is that every one of the solutions we talk about, these are things that we have implemented in our own factory. So we walk the talk, so to speak, and we can stand behind the use of these procedures and solutions. So what are those 4 steps? When we start to create a digital factory, we first need to collect the data. So at its source, we need to extract data out of a process. The next step is we need to transport that data. We have to pull it off the factory floor and we have to move it to either a higher level system or to another layer of the enterprise. Along the transportation portion, we need to secure that data. So in order to secure it, that would be the cybersecurity mode, which again goes along with the transportation portion of the step. And lastly, we need to do something with the data. And so here we go. We've got your 4 basic steps. This is not quite rocket science, and that's the whole intent here. For each of these steps, we'll now do a little deeper dive into what it takes to implement these in your factory. So we're going to start at the end, because this is where the question has to first be asked. In order to apply this, we really need to know, how are we going to use the data? And this is quite frankly the hardest part. What we found with other customers is that the reluctance to start comes in many different forms. It's too expensive is a perception. It's too complex. It is difficult to determine the ROI. On the last item, I have to agree with that. It is very difficult to determine the ROI, except in the applications related to energy. When we get some data out, we know we can improve processes. We know that intuitively, but sometimes it's hard to monetize that. And I think everyone in our industry is struggling a little bit with that concept of monetizing it. What I do know is that once a customer does it and applies it, they intrinsically know the value. So this one, I know oftentimes when we're trying to do projects, we have to go seek budget in order to get a budget. We have to determine the ROI or present the ROI to the investment. But at the end here, I'll explain why that may or may not be necessary in this particular instance if this concepts are applied. So some of the justification for starting the journey can be tied back to things such as quality improvement, traceability. This is probably one of the largest ones that we've seen from our use case examples, is that customers need better traceability, which again is related to quality improvement. Much of what we do is tied to the automotive industry. Our group specifically is focused on automotives, both end users, the OEMs, as well as tier ones. And traceability and quality is everything. We'll talk a lot about things like being in containment and having to do 100% sorts and trying to find solutions around that. Those are pretty easy projects to justify. We hear the term OEE, overall equipment effectiveness. This is started out as preventative maintenance, then it became predictive maintenance, and now it's really more holistically looking at the machinery or the capital equipment that we have and determining its uptime, its efficiencies, how much is it running, when is it down, why is it down. A little bit more deeper dive. So this would be another justification for starting the journey, is that you need more machine uptime and equipment effectiveness, a better utilization of your capital. Anomaly detection would be looking for variations. If we know what good is and we create a window or a signature of what good is, anomalies would be deviations outside of the norm. Now, historically, we already do that, but we do it in a very set point type control way. It's either on or it's off. It's a go or no go type of gauge. It's very digital. By having more data, we can dive deeper into the process, which then in turn provides us a signature or a better view of the process. And this is often the case where when we do ask somebody, what is your challenge? They're like, I just need a little bit more information to look at this problem a little bit deeper, rather than the information I have now, which is a gauge that says I'm good or it's bad. I mentioned earlier, energy conservation. This is probably the most overlooked area in which digitalization can be applied, but it's also the easiest one to calculate the ROI, because we know the cost of energy and we know that if we fix a problem, we are going to save X number of dollars or units of energy. And so this one is the easiest one to, I wouldn't say to apply, but certainly to justify early in the process of starting down your journey. And lastly, this is one that we've implemented pretty strong. And just 3 short years ago, most of our work instructions came in the form of paper work instructions out at each assembly site or assembly station. And so with digitalization, we're just able to collect the existing data that's already there and then visualize it in a way that helps to automate it via screens now in front of the operators, rather than paper type work instructions. And it was really doing nothing more than taking the existing data that was there and processing it and visualizing it in a way that could create a little more animation. Now that can be taken to the next step, is that you can apply some artificial intelligence that can actually guide the operator into how to assemble or follow those work instructions without having to read them or look at them graphically. So some of the terms as we begin down the process of using the data. So again, we collect the data, we transport the data, we secure the data, and we use the data. And we're starting at the end because we have to answer the question up front, what is it that we're trying to solve? And so first I like to talk about just a few terms because, as you know, as we get into just the word IIoT, there are lots of acronyms and there's lots of words around Industry 4.0 and digitalization that most of you probably already know, but I'd like to just go through some of them very briefly as they apply to this particular topic. So a server is a device that is a PC, if you will, a computer on steroids. It usually has very high horsepower in terms of its processing capability. It typically has redundancy or dual drives so that if one drive is to fail, it has a backup drive because it has to have 100% availability. A server can be either local, it can be what they call on-premise, it can be in the building, or it can be remote or off-prem. Many times when we talk about the cloud, we're talking about servers that are off-premise, which takes us to the next subject of what is the cloud and where is the cloud? Well, the cloud is just a group of servers that are hosted somewhere remotely. The cloud can be hosted by your company itself, or it can be hosted by a third-party company. Companies like Amazon, Microsoft, many different companies have, I guess, cloud-based services in which they offer mass data storage, analytics, and other tools. Analytics is just that. It's the analysis of the data to produce a result that we can then visualize and or take action upon. SCADA is an acronym for Supervisory Control and Data Acquisition. So this is taking the data and visualizing it in a way, performing some analysis on it, and then sending that data back. It also typically has what they call historian content. So it will log data, and all of that is done physically on a server. The MES is the manufacturing and execution system. So we have the plant floor. Then the next layer of our architectures are usually the MES. This is where all of the manufacturing information resides. So it's saying this is the part that's going to be built. These are the components that make it. These are the instructions that it takes to produce the part. And when the part is made, it collects the data. The next layer above the manufacturing and execution system is the ERP, the enterprise and resource and planning. This is the back office stuff. So the MES will typically feed into the ERP, which has the overall picture. This is the upper level office and enterprise level software. So this would be things like BON or SAP is the big one in the ERP layer. So again, those are some of the terms that we'll hear when we're using data. So the first question is, what is the problem that I'm trying to solve? And this is a question that we usually ask of one of three people: the maintenance folks, the quality department, or the IT department. Forgive me, I forget that. So this can be asked of the of maintenance, quality, or manufacturing engineering. There's never been a time I've walked into a plant and haven't asked a quality person or a manufacturing engineer, do you have a list of problems? And they typically pull out a piece of paper that's about 2 feet long, and they have a list of problems that are on their to-do list to solve. So finding a problem is usually not too much of an issue with the folks in that space. So the next question is, once you determine what the problem is, and it's going to fall under one of those categories, is it equipment uptime? Is it traceability that I'm looking for? Is it quality control? Is it energy analysis? Once you determine what that process is, then we just need to know what information is needed. What is, based on the problem, what is the information that is related to that problem? And what we find at this step is there isn't a ton of information that's needed. It's not like, I think the conception is, I have to send all of my data. I have to pull all the data out of the process. I have to send it all somewhere and then do the analysis. And what we find is, no, I've already got 2 or 3 pieces of information that I'm looking at already. I just need maybe one more piece of information to help fill in the gaps to complete the puzzle for me. So for example, I may have set point control. I know that this thing is good or bad, on or off, but I don't know that some other external factor is influencing that. And I just need that one more piece of information to then understand how it relates back to my problem. Once you determine that information, then where's the information found? Is it in the existing process, which most of the time it's already there, it's already in the process. So how do I extract that? And or do I need to add, as I described earlier, just that one more piece of information? From there, then on the other side is what output is desired. Where do I need this information to go? Do I need to handle this locally? Do I need to make it visible across the organization? Do I need to store the data? So what type of output is desired? Do I need to simply just turn on a light and show the operator, hey, I've got a problem in this station? So it can be simple or it can be complex, but you have to think about both the input side and the output side and what is the result that's desired. Then how to visualize that. Is that visualization done locally? Is it done remotely? Is it done in the cloud with remote access to that cloud? Does the data need to be stored and logged? Within automotive, there's a big trend to get further and further or more finite, I would say, traceability. So there's a concept out called the digital, I think you call it a digital license plate, if you will. So for every part and every ultimately vehicle that's made, the traceability and tracking of every component level part is there and it's stored somewhere, so that once that vehicle is complete, assembled, and gets a VIN number, it can go back, they can go back in time and determine every nut, bolt, assembly, weld, and capture all of that data from end to end. Today, most of the traceability is related to the safety features. It's the things like the airbags and the seat belts. Those have to have complete traceability and throughout the process, and then ultimately stored and registered with the vehicle. But the industry is trying to get more and more finite, which obviously is going to create more and more data and the need for storage of that data. And lastly, who needs access to this? Is it simply just to alert the operator at the local station, or does it need to go to management? Does it need to be on a mobile device to let a remote worker know? So who needs access to the data is part of the things we need to consider when we're looking at using the data itself. So I'll give you a couple examples of where we've done that. And you'll see throughout these use cases, you'll see some common both themes and why the customer started the process of digitalization, and also under kind of what categories they fall. As I mentioned, we collect the data, we transport the data, we secure the data, and then we use the data. It could be one of those things, or it could be all of those things. And typically it's not just one. We don't just collect data without obviously using the data. We don't often collect data without transporting that data. And anytime we transport the data, obviously we want to secure the data. So here's a customer who was getting false rejects. Now, this particular customer is a machine builder, and they build machines that assemble parts, very high precision parts, and in the process of assembling them, they also gauge or inspect the parts. The parts themselves are, as I mentioned, are very high precision, and the process is very high precision. We're talking micron type conditions and measurements that they're looking at. And so what was happening was, and how the conversation started, is we were talking to the customer and he said, I'm struggling with, our customers are struggling with our machines being down because we are rejecting parts that when we gauge them in process, they're failing. Yet when we gauge them mechanically, they're fine. So in a sense, they are false rejects. And what that resulted in is machine downtime. So this would fall under the category of an OEE application. The equipment utilization was being diminished because of false rejects. So they had simply a set point type control. They were just manual adjustments to the pressure. And each time the parts were rejected and they went back, they would have to manually adjust pressures to get the parts and the inspection back into tolerance. But they knew that there had to be some other external variables. They also knew, because they make machines for a lot of different folks, and sometimes they have to go into existing, let's say, brownfield assets. They're going to tie a test piece of equipment to an existing machine. They needed to be able to have a wide range of interfaces because they didn't know whether it was a Rockwell PLC, say with Ethernet IP, or a Siemens PLC with Profinet, or some other protocol that they had to interface to. So they needed a wide variety of inputs. And lastly, they said, well, we think that temperature is the issue. And this is where developing that signature was really important to them. So they intuitively knew, or thought they knew, what the problem was. They just didn't have the data to support what they thought. So they said, well, let's look at climate variables, but down the road, let's also make room for expansion of this system. So it had to be scalable as well. So it had to serve a wide range of interfaces, and it had to be scalable. So the solution we came up with, on the left, you see this was the existing system. It had a PLC with sensors, I/O, and drives. There was a switch there in the panel. So we took our data collection device, which we call PLC Next, and it's an open source Linux-based machine that can connect to any type of input. So in this particular case, it was a Rockwell PLC, so it had to consume data from the Rockwell PLC via Ethernet IP, and it also had to add a device to it. In this particular case, a weather station that had both barometric pressures, temperature, etc. Now that had an interface called a Modbus interface. So we had two different interfaces that we had to bring through a central data collection device, and then collect that data, analyze the data, and then send that data up to the MES, which then allowed it to provide process feedback. So as the temperature began to increase, they knew that they could change the offsets variable without shutting the machine down, rejecting parts, and then manually going and changing the process. So on the right there, you see some of the benefits they received. They got formatting of the data, which is really important. So we had two disparate types of data that we had to bring together in one common format, and then send that out another language to the MES layer. And the main thing here in all of these situations is, and the reason why when we use data, when we collect data, and when we use the data, we often do this through a third device, or a second device, if you will, a little black box. And that's exactly what this particular customer says. He goes, if I could find a little black box that would help me get this data, add some more information, and do it for under $10,000, I would be ecstatic, because that would solve my problem. And that's exactly what we had. But it had to be able to consume and produce data from two different sources, and then send it out in a completely different language. So that's one example. That was a machine builder who was struggling with machine downtime related to external variables, in which just literally one more piece of data helped them to solve their problem. This next one is a tier 1 supplier. They make interiors, and they were in containment. For those not in automotive, in containment means when a customer, when a vendor ships to automaker parts that are defective, they are then forced to contain the parts that they're producing, do 100% sort or inspection of those parts before they ship it, while they determine and come up with a solution to prevent any future rejects going forward. So this customer was stuck sorting at a very high cost all of their parts before they would ship them out. The issue here is they injection molded parts in their plant. Those parts then went into an assembly. So you figure in an interior, you have a dashboard, and behind that dashboard or the instrument panel is a series of air ducts, and they injection mold these air ducts. Well, there was no traceability of the components that went into the overall HVAC assembly. So what they needed was a device to help to, number one, get information from the injection molding machines. Number two, connect to their MES, to the manufacturing and execution system, saying, okay, I'm running part ABC. I need to identify this with a barcode label. They then in turn needed to verify that the part was produced, the label was applied and verified with a scanner, and then that data sent back to the MES to say the part was complete, and that gave them the traceability. So the solution involved connecting a barcode printer that got its information from the MES. They needed to make sure that this information was secure, because connecting the factory floor to the MES layer is where cybersecurity is required through the data transportation. They also needed to be able to expand this into other applications. If they, again, just like in the past, they wanted to have built-in expansion so that if they needed one more piece of data, they did not have to buy a whole new solution. So what we provided them, again, was in this particular case, a little black box in which we had our PLC Next, which is the data collection device, a small HMI, so that provided local visualization so that the operator could engage. So this provided them somewhat of an automated work instructions, which told the operator the label has been printed, now verify. So they had to push a button on the screen. They then had to grab the barcode printer, or I'm sorry, the barcode reader, scan the label, then verify that it was read, and then that data was set up to the MES, which said the part can now move out of the station, and it has now got traceability towards it. So again, it goes back to the questions. How much data did I need? Not a lot. I just needed to know, was that injection molding machine complete? So I extracted data from the molding machine, which had a PLC in it. I then needed to interface to the barcode printer and scanner and or laser marker in some cases, and also tie to the MES. So I needed this third-party device to interface to the systems. And again, all of this needs to be done without disrupting the existing process. Some of the data that's here in the molding machine, if I were to go and attack it that way to modify the machine, I would have to take the machine down. We're able to add this device and extract the data, yet keep this machine running. I look at any piece of plant floor equipment that we attach to, that machine is printing money, and we don't want it to stop printing money. So we want this, whatever we do when it comes to data collection and using the data, we want to do in a way that's non-intrusive and does not create any disruption to the existing process. So that's one of the factors you need to consider when you're both using the data and collecting the data. So that's a little bit about the end game. Here's a couple examples of how I used the data to improve my process. The first one to show how to help improve equipment uptime or OEE. The next one in terms of improving my process, my quality, and in creating traceability of those parts throughout my manufacturing process. The next step in the beginning, if you will, is data collection. Many of you have probably seen this layer or this pyramid, if you will, that we talk about. So that at the base of the pyramid, we have our production process, and there are things such as temperature sensors, robots, gauges, etc. These are all the sensor level devices out on the factory floor. They in turn connect to PLCs, CNCs, robot controllers, again, still at the factory level floor. But the gray areas that you see in the boxes are what we consider to be data silos. All of this data is very siloed in each of these layers. It does not necessarily and historically move from layer to layer to layer. But ultimately, we want in a digital factory, we want seamless integration of that data up and down through the enterprise. Around the periphery of the pyramid, you see all these words, if you will, and what these words are various protocols and terms that are used to both to move data on the factory floor. So things like Profinet, EtherCAT, Modbus, CC-Link, Ethernet IP. These are all what are considered to be protocols or languages that various PLCs and machine control devices, these are the languages that they talk. At the top, you have very high-level programming tools that are used, that things like Python or C++, SQL Server, Node-RED. These are high-level languages that we use to do analysis of data. But what we're trying to do here when we collect the data is to span these gaps between both what we call the operation layer, which is down at the plant floor, and the IT layer, which is somewhere at the ERP, MES, and cloud layer, and take that data and move it out of the silos and into the enterprise so it's visible throughout. So some of the terms to consider when we're looking at data collection, we'll hear the term edge and gateway. And again, this is the Mike Brooks definition of the two terms. A gateway is one that simply takes the data from point A and moves it to point B. It really doesn't do any analysis of the data. It is a gateway between the factory floor and some destination. That destination can be a local server. It could be a cloud-based server. It could be a SCADA system, such as Ignition. It simply acts as a gateway. Whereas an edge device does something with the data. If we just move data, we'll get to this in the transportation layer, but we're moving a lot of data, and whether that data is used or not is of question. So as a gateway, we're sending all the data to the cloud, so to speak. The efficiencies of that may or may not be the best. Maybe that is the best thing. Maybe I want to know, or I want to have all that data and then access it at some point. But most often than not, and it goes back to what is the problem that you're trying to solve, I only need a few points of data. And a lot of that data I can process right at the edge. So an edge device will take the data from point A. It will then apply some code or some math to the problem. And then, only then, it will take the output of that result and send it to a higher level system. So I'm minimizing the amount of traffic that I have on my network by processing the data on the edge. Protocols we talked about, those are the various languages that all the different devices speak, and there are many different protocols. So I look at the factory floor like the United Nations. There are people speaking German, French, Italian, etc. And we have to be able to go in and talk those languages. The next term, normalize the data, is then what we do with that. Normalize means I take it in one format and I normalize it and put it into another format that the higher level system can consume. Because I can't take raw data straight off the factory floor that comes in, let's say Ethernet IP, and send it up to the MES layer, because it doesn't understand Ethernet IP. I have to put it into a format, the MES layer. And typically you'll hear things like MQTT or OPC, OPC-UA, or MySQL are formats that the higher level systems understand. But something has to be in the middle that takes and normalizes that data between the disparate sources that it comes from and the destination that it's going to. And lastly, an algorithm. An algorithm is a little bit more complex math. If you look at most PLCs today, they perform very simple math functions. They do addition, subtraction, multiplication, division, etc. Algorithms take a sequence of math equations and combine them together. They are the basis of making decisions, and it's always a scary word, but they are kind of the basis for artificial intelligence. And that is simply just taking a little bit more data, doing more complex math on it, and doing statistics and analytics. So in order to do true analytics on things, you typically need an algorithm. And the reason that you can't do it in the existing infrastructure, and usually you need a secondary black box, that black box can be a PC, is that algorithms are typically programmed in higher level languages that are not found in a traditional PLC. So thus I need to at least have it come into some form of a computer or PC-based system, whether it's Linux or Windows-based system, that I can then perform advanced math on. And that's done through higher level languages. And again, as I mentioned, as part of Digital Factory Now, we have training on all of these topics and very deep dives. So I'm not going to get into that, and I'm personally in no position to do that, but we have a lot of smart people that can help you with some of these deeper domain dives if you'd like. So some of the things to consider when you're looking at collecting data. First off is what are the inputs? What are the things that I need to connect to? Many times it's simply just the existing machine PLC. I can get data out of that. All the sensors, all the IO, all the drives are typically connected to that PLC. So the majority of the data is going to be in that device. I just need to extract it. Now, there may be a secondary device that's connected that I need to add, just like in the example we showed you earlier, where we have a PLC running the machine and they needed to add a weather station. So then the question is, what do these various devices, what protocols, what languages do they speak? And in our case, we don't care. We're kind of neutral. We're like the United Nations, speak the various languages. We'll consume the data, we'll normalize it, and we'll put it in a fashion that somebody else or some higher level system can deal with. Or additional inputs needed. Statistically, we found, and again, based on our use cases and things like that, very little inputs are really required to make decisions, in the order of less than 10 type of inputs. So it goes back to our at least our observation and our perspective is sending all your data up is not necessarily. I just need 3 or 4 pieces of information or inputs to look deeper into my process and begin to make some decisions. It doesn't have to be an all or nothing thing. And then where does the output go? So I've got my inputs to determine the protocols, the languages that they speak. And then the question is, where does that information go? What do I need to do with the output side of it? Does it go to the MES? Does it go to some SCADA package, supervisory and control, visualization system? Does it really just need to reside at the edge, and I just need to turn on a light to alert the operator? I mentioned it earlier. It's really important, we feel, to not disrupt the existing process. As I mentioned, the machines that are running on the factory floor or capital should be at 100% utilization, and they should be printing money. And if they're not running, they're not making money. So anything we do to collect data, we want to make sure that we're not disrupting the existing process. And in order to get data out, many times in other approaches, you have to go in and you have to shut the PLC down, you have to reprogram it, you have to add additional hardware, software, drivers to it. Well, all of that represents downtime. And our approach is to do that without disrupting the process. Next, what packaging is required? You saw a couple examples there. Do you just need a little device, a little gateway or edge device? We make that in different form factors, PLC-like platforms or small box PC platforms. Do you need it put into a box? Do you need a power supply? Do you need an Ethernet switch to make it all work together? That's part of the consideration that you need to make or ask when you're doing data collection. And is it scalable? This is one thing that's come up with a lot of stuff out there. Is it does what it does it extremely well, but that's it. It's very limited. It's not scalable. It can't expand if the application requires more. I think all of you have seen in your personal experiences in working in factory automation, there is a concept called application creep, right? It starts out, we want to do this. And once you're able to do that, it's, oh, by the way, can it do this, this, and this? And we want to say yes, because we want that scalability built into the solution to begin with. We don't want to paint ourselves into a corner. And lastly, with the output side of things, where's the data? Is data storage required? And if so, where do we want to do that? Does the data need to be stored on a server? Can it be stored locally and then served up later? Is it done kind of at the edge? Is it done in the cloud? Is it done, on a local basis to another server on the factory floor? So it's basically, what are the inputs, what are the outputs, and how do we want it to look? And from there, then we can determine what that data collection device looks like and what programming is going to be required to make that happen. So a couple of more examples of how we do data collection. And again, for each of these examples, you're going to see both the collection of data, in this particular case, the transportation of data and the usage of data all in one. So this particular customer is doing a heat treat process in their plant, and they had analog gauges, which is very common in the heat treat process. There are a series of gauges out there, and we're controlling flows and temperatures, and it's all done manually with gauges. It's been done like that for a long, long time. There's a lot of that installed base out there, but this is the need in the driver to transition to a digitalized interface, because it requires and results in machine downtime in order to make adjustments. Or if things start to drift, then we're shutting down the process to try to fix it, to get it back into a running state and printing money for us again. So by digitizing it, we can do a few different things. We can look at real-time data, so we can analyze the process and watch it. Through that data, we're now collecting and developing a kind of a signature of what that process looks like. If you think about things like heat treat processes and just process things that are processed in general, as opposed to discrete manufacturing. Discrete manufacturing is where I produce a part, think it's kind of an on-off type conditions. Processes have flows and temperatures and a lot more variability. And the people that operate that equipment, they're very well trained, and they have to kind of manipulate each scenario, and they have some intrinsic knowledge based on their own human real-time information. So it's really important in the process world that we begin to get digital data so that we can automate some of that human domain knowledge, apply algorithms to it, and automate that the variability that exists within process type operations. So the solution that we provided there, just like everything, it had an existing PLC, in this particular case, a Rockwell PLC that spoke Ethernet IP. That was the protocol. It was connected to a plant floor MES. And they wanted to also send this data, store it, and put it in the cloud via a protocol called MQTT. So on the left side, was the existing infrastructure. On the right-hand side were the things that we added. So we provided a little black box that had our PLC Next data collector. We also added these energy meters. So there were current transformers that looked at the heating elements that were connected to an energy meter. This energy meter monitors things like current, power consumption, etc. And then it exchanged that data via Profinet. So here's a case where I had Ethernet IP, one protocol coming in. I had Profinet, another protocol coming in. And then we had MQTT going out to the cloud. But this provided real-time information. It allowed them to maintain and manipulate the process remotely. It also allowed them to do it in real time, whereas before the only adjustments would occur after they had some machine downtime occur. Another example of how we would do a data collection example is this particular customer is a manufacturer of car parts that are, we call them body structure parts. And in the process, they weld different parts together. And what they were looking at was the tolerances of their welds, and they were having problems and were in containment. We talked earlier about once we begin to have quality problems and we ship something defective to the car manufacturers force the supplier into a containment where they have to sort that. Very, very expensive. So what they needed to do in this particular case was somehow monitor those welds. And in this particular case, they did that through a vision system. The vendor lock, this is something we talked about a little bit earlier, in that when the customer first went out to look for a solution to this, the only thing they were getting were proprietary, expensive, single vendor solutions. So they were not open, they were not modular, and they were not scalable. So this customer really desired something that was open, something they could own, something that they could add to in the future if they wanted to do more than just simply inspect these welds, but add more features to it down the road. And they wanted to do it and needed to do it on the edge, so to speak. So they knew they did not want to change their existing processes. They wanted to do this external to those processes without being disruptive. So this one is a little bit more complex. You had this is the right side, the existing operations where you had a PLC, you had some IO, robot controller, weld controller, all talking to this PLC. So we added our data collection device. It went in and extracted data from the PLC, as well as some of the information from the robot controller. It then created the interface to the camera, where the camera was collecting images. We then used, or this particular customer used AWS, which is Amazon Web Services, and their IoT Core and Greengrass to do the data analysis of the camera. And then from there, we sent that data back through the existing controller back up to the plant MES. So this allowed them now to do offsets based on offsets to their weld controllers. So it allowed them to change their ranges based on the condition that the customer saw on the vision system. So we looked at the part, we determined it wasn't just simply pass fail. They were able to develop a signature of what was good through some, I guess I would call it low level artificial intelligence, and then create windows saying, okay, if we're starting to drift within this window, begin to create more weld temperature or more dwell time. And so we created this closed loop system for them that helped to address their issue and resolve their quality problems. The next step in the phase is to transport the data. And as I mentioned, throughout these various steps here, you see that these things are tightly interwoven. So we collect the data, we typically have to move the data, and usually that's from the plant floor up to the factory information system or MES layer, excuse me. But this is, to me, one of the most often overlooked areas. And I'll use the I love the story every Christmas called The Christmas Story, the movie. Maybe you've seen it. And you watch the father takes his Christmas tree and constantly plugs in more and more Christmas lights, and eventually he blows the fuse. Well, quite frankly, that's what we see a lot on the factory floor. Is there are Ethernet switches out on the factory floor, and folks see an open port and just plug a device into it and just keep plugging. Well, as long as there's open ports, I can add one more thing, whether it's another interface, it's an HMI, whatever that is. But eventually you're going to blow the fuse because you're just putting too much information through that device, or the device isn't rated or designed to take all that data in. The main thing here, and there's a lot here, because as we get into network architecture, I will only say that Phoenix Contact, Rockwell, Siemens, we all have, I think, very good people that can help you architect your network. And it's a really important step. I've got to stress, this is the point at which the IT community absolutely must be engaged. So the sooner you engage the IT community, you're going to need their help whenever you do digitalization. I know there's always the rift between IT and OT, but those barriers I see increasingly coming down, because they have to, in order for digitalization to work in our future and in our factories. We have to all work together, and IT does want to work with us, but they have to manage risk. That's their job, and they need to help design these systems so that they can be expanded and they remain safe and secure. So there's a lot going on here, but I'll talk about the factory floor. As I mentioned, we are factory automation folks. We come from the factory floor. You've got Cisco, which is traditionally at the enterprise level. Cisco devices can be deployed on the floor in some levels. A switch is a switch, but you want to look for things like industrially hardened switches. You want to look for things that support the various protocols. There are different protocols that exist on the factory floor than they do in the office environment. So some of the terms we talk about, and really to me, what it's all about is bandwidth. If you just have a few devices connected, you're probably not worried about bandwidth. Going back to the Christmas story, at some point I'm going to plug in one too many things and my network's going down, and that's a big problem. And why does it go down? Because I've just consumed all of my bandwidth. Bandwidth is the ability to move data at a certain amount of data at a given speed. And we want to move, our goal should be to move as much data as quickly as possible. But as we continue to add devices without proper topologies, we begin to degrade bandwidth, and that's not a good thing. On the factory floor, we find two different types of Ethernet type switches, unmanaged and managed. And very simply, unmanaged switches take all of the data in and send all of the data back out. There is no management saying that this information is intended to go to a different person, individual, or device. Whereas a managed switch has, just like the name implies, it has some management tools in it. It's like a traffic cop. It says this piece of information is coming in based on the packet. It's intended for another device, and it routes or it sends that information to that device only, and rather than broadcasting it to everybody on the network. In doing so, and I have a very clearly defined path for the message, and I'm not broadcasting it, thus I'm not consuming bandwidth. And lastly, we always hear about OT and IT. So OT being operation technology, this is the factory floor. So you'll see that pyramid, and there's usually a line right down the middle. The devices below that, below the line, are the OT, or the operation technology, the factory floor or factory automation side of the equation. From the MES to the ERP to the cloud is typically to the enterprise is the IT layer. And we have to span those two gaps. Historically, it's always been IT is here, OT is here, and these two devices don't talk. But again, in order to realize any of the benefits of digitalization, those barriers have to come down, and we must span this OT to IT divide. So when we talk about data transportation, it's pretty basic. We're trying to maximize bandwidth. So how much data? Now, I know most people in places we go, it's not like you can't necessarily quantify this. It's a relative conversation. Am I moving a lot of data or a little bit of data? I'm not asking in how many bytes of data are you moving and doing a specific calculation. How far? That's another factor. Again, bandwidth being how far, how fast, and how much. Distance plays a role, and I need to break that up. How fast? Are converters required? There's a lot of stuff out there. Very rarely do we have a clean sheet of paper where we're designing networks. We're typically going into an existing architecture and adding devices or trying to improve it. And on the factory floor, there's a wide range of stuff. Some of the stuff may not even have Ethernet connectivity. It may be old, what they call RS-232 or 485. Well, we need things like converters to convert that information that exists in one format, say RS-232, into Ethernet-based data and protocols. Are there connections to other IT devices? So what we put on the factory floor at some point is going to connect from the OT level to the IT level. And we know that the IT level is largely a Cisco environment. So we've got to make sure that the devices we put on the factory floor are compatible with the office and the IT infrastructure that is Cisco devices, because the IT group needs to manage those devices throughout their both network and the enterprise. So the compatibility to other IT devices is very important. The topology, as I mentioned, plays a big role in this. Normally we just plug stuff in until it works or doesn't work. But in the architectures, we begin to segment these things with different topologies. Is redundancy required? Increasingly, on the factory floor, we want 100% uptime. And if a device ever goes down and I take that device offline, does the network go down? If so, that's a problem. So we have to design in redundancy so that if I pull this device out, all the traffic is rerouted in another way in a redundant fashion. But that feature has to be designed in to the system. And lastly, where's the management function and where does that exist? It exists in every IT or the IT organization within every company. So how much level or how deep is the IT community in your organization coming down in terms of managing the devices right down to the factory floor? If they're not today, they will be soon, because as I was told by a number of different IT folks, if it has an IP address, I own it, because they have to manage it, they have to secure it. And we can either fight them or we can accept them. When I say I came from I'm a controls guy and I came from the controls world, and I've lived for a long time in this us versus them. But we really need to look at the management side of the IT devices and accept that. So a couple examples of how we transport data. You've seen that in some of the other examples, how we move the data from A to B. This one in particular was unique, and it really started out of a cybersecurity issue, but you can't really isolate cybersecurity from data transportation. We should be securing the data at every chance we get. Every device it connects to should have some form of security built into it. But this particular automaker was a victim of ransomware, excuse me, which shut down their plant. And the reason being is they had a very old architecture. This is the case where they just kept adding machines over time and connecting them without any real architectural thought process to it. The method to keep it secure from IT had been to just keep the plant floor data off of the IT level network. So that creates all these islands of automation. Each machine, cell stood on its own. There was no insight into the process as a result. And there was a significant cybersecurity attack, which was illustrated by the fact these guys were held ransom due to a hack. And there was downtime because they didn't have any ability to visualize their process. So we were able to go in and take a look at the existing network, which we call a kind of a hub and spoke system, which is not, by today's standards, this is what is sometimes many times typical. It's just, I'm going to just keep adding devices and keep plugging things into the network, but without a real structured or topology or approach. So we helped to architect a new system for them, which provide them benefits not only of redundancy of their network, so that if any one of these devices go down, it doesn't take the whole network down. We did segmentation of the networks so that we isolated the various networks. Off to the left here, this device here was our PLC Next. It provides the overall visualization of the network. It tells the network's health, who's going on, who's coming off, and then it has remote access to the IT level Cisco management system. So it manages the factory floor information, and then it sends that device management data up to the enterprise level. And it also provided them remote access through mobile devices. Now that we secured the network, now I can allow for people to get on board because I can grant them access and or deny them access through cybersecurity devices. So this really helped improve the process. It took away their vulnerability. It greatly improved their bandwidth, and it's designed now that it's very scalable should they add any more devices down the road. This one is a little bit simpler, and it's one that comes up quite often, and maybe you have the same challenge sometimes. Up till now, everything we've talked about has been a wired device. It's an Ethernet cable that goes to a switch somewhere. But many times we're adding devices on the factory floor that to run a wire or cable to it, an Ethernet drop, is too costly or it's prohibitive based on its location in the plant. In this particular case, it was in the body shop area of a Japanese automaker, and they were adding torque tools. These are the tools you see hanging from a string. They're usually connected to a little black box controller, and they control the torque for attaching nuts and bolts and things like that. Well, they were adding these torque tools to their process, but they had no way to connect to them. And in order to run cables, they were not originally part of the budget to get the interface to the torque tools so that the enterprise level could send information down and get torque values back. So bottom line is they needed a wireless solution that would work in their plant where there were already wireless stuff. And so they needed to have security of the data. They needed to be 100% reliable. Because it wasn't part of the budget, they needed to be very cost effective. And because they already had existing wireless routers out on the factory floor, we needed to be able to talk to those and be compatible with, in this particular case, Cisco devices. So it was relatively simple. We have a little, we call it a radio client that's 802.11, which is the WLAN or the Wi-Fi enabled devices. This connected to the torque controller right here, and then exchange data to the plant level access point that existed on the factory floor, which then sent data up to the ERP. So very simple data transportation, but done in a wireless format. So many times people say, oh, I don't want to do wireless. But this is where if you get involved with IT and get their buy-in and have them be a part of the discussion, we find much greater success in doing that. And success in terms of reliability, it works. It's just you have to get the buy-in of the IT group because they're the ones that typically are not, they have to be sold on this technology. And lastly, we need to secure the data. And threats come in lots of different flavors, and there are whole seminars, and we've just completed October was Cybersecurity Month, and we have folks on staff that are have master's degrees in cybersecurity and do a lot of speaking engagements. So I am certainly not that person, and all I know, and I think we all know based on stuff we read, these threats are everywhere. For the longest time, they really didn't affect us on the factory floor because we being factories weren't a target for hackers and things like that. But now hackers want to hack anything and everything because it's just a win. And quite frankly, factories, because they didn't consider cybersecurity in their initial designs, were very vulnerable, as we saw kind of with the example I showed you earlier with the ransomware attack. Their networks were very susceptible, and it could be your plant as well. So these threats come, some of them are malicious and some of them are innocent. Somebody walking up to a port and plugging in their PC because they want to go in and program it can introduce a threat. And unless there is cybersecurity methods put in place to either allow or deny access to that device, then you have a threat. So one of the distinctions we always talk about is what's the difference between the OT and the IT layer? And in the end, it's all kind of the same. It's data, but we look at the world a little bit differently. So we're all concerned about things like confidentiality, integrity, and availability. So is my information confidential? At the enterprise level, yes, that's the number one priority for the IT, is keeping confidentiality of the information and the integrity of that information, lost data packets, things like that. I want to maintain high integrity. The availability is the least important thing. Not to say it's not available, but availability means, is it up 24/7? If we look at our office network, if a laptop goes down, it doesn't take down the network, it doesn't disrupt production. I simply reboot and start back up again. So availability in the IT world is one of the lowest priorities. Where if we look on the OT side, availability is the number one thing. We have to keep production running 24/7, no downtime. That's it. When it comes to data transfer, availability is the highest priority. Integrity, again, of the data is very important in both cases, and confidentiality. So this is one of the distinctions between OT and IT, and why we use different devices and talk different protocols. There's also some standards that govern the different areas. So there's an ISO standard that governs informational technology, yet a different standard that governs the security of plant floor data. And these two things are not mutually exclusive, but they are independent standards to which they're managed. And the IT community has to deal with both of these, just to be aware that there are these simple differences between the two worlds that we live in. Some of the terms related to securing data, router is just that. It routes the data from point A to B and goes across two different networks. So when I cross the IT to OT layer, I have to have some form of a router to say this information can go from point A to B. Next, I want a firewall, something that says and prohibits the movement of the data from one device to another with rules. So a firewall you apply rules to, and you say, I either allow for access or I don't allow access. I allow you to go on this portion of the network, but not that portion of the network. I allow you to talk to this device, but not to that device. And lastly, a VPN is a virtual private network. This is usually used alongside the ability to remotely access devices. So it takes a private network that exists within the enterprise and extends that out beyond the building or the enterprise into the public domain, such as the World Wide Web. So it allows people to remotely access through the World Wide Web into a private network based on a very limited set of credentials. So a VPN here is a tunnel that allows us to come in through a very specific pipe and window into the enterprise. So we talked about, when we're considering these things, what are the threats? What are the age of existing systems? Because as an example, if we have things like personal computers or factory floor computers that are out there that are running older versions of Windows. Those are threats because Windows doesn't update them any longer and they're no longer secure. How is the data going to flow? Is it just one directional? This is the way to make data very secure, is we only allow the data to come from the factory floor out, because that's really what we need. We want to push the data. We don't want somebody coming in. So a router allows us to write those type of rules and create those firewalls. It says the data can go out and it can go up to the MES, but somebody coming from the outside in is not allowed, and it gets blocked at that machine. Who has that authorized access? How are we going to segment our networks? Do we do it in cells? Do we do it individually? And who has management of that? Again, usually the IT community. So a couple examples of secure access that we've provided. This particular customer, this was a very large multi-year project in which the goal was to provide remote access to their machinery all around the world through a cloud-based portal in which they could connect via a VPN to devices on the factory floor. So it started out in a relatively simple point-to-point. I need to come in through a VPN, go down to a machine. We do that all day long with small appliance type devices, but this particular customer, who's an automotive supplier, they wanted to be able to do this anywhere in the world and get visualization of their processes. So they really needed to architect their complete factory floor networks for both maximizing bandwidth and securing the devices on the floor. So what we helped them to do was design basically a network in a box. So in that box are managed switches, which provide us the ability to segment the various devices out on the factory floor. We call our mGuard, which is a router. It's a security appliance. So that provides the VPN connection. In the cloud, we have a server-based VPN that they can remote into. And we segmented all of their cells and machine equipment on the factory floor. This next one is one we just started working on. This is a global manufacturer of spices, and this is an energy application. Now, they wanted both the ability to visualize data globally as well as secure the data globally. So similar to the last application, but they had spent the previous 2 years looking for a open source type of solution. Everyone they had approached up to this point was a highly proprietary end-to-end single vendor solution. And they said, we just don't, if we're going to do this and we're going to make this investment over the next 5 years, we want it to be open source so that as technology moves and vendors change, we can adapt and make use of best case practices and solutions that are out there. So we were able, and we started this process of helping them to architect that system to help bridge the OT to IT gap, to allow for expansion and to interface with the wide range of protocols that we find on every factory floor over time. So again, this was related to the primary driver here was energy management, and it started out with simply managing or monitoring the energy of each machine. But over time, they wanted to be able to add facility power, temperature, flows, pressures from things like compressors and so on. So they needed to be very scalable and add more and more devices as time went by. So to recap, we've talked about the 4 pillars here of data collection, data storage, data transportation, data security, and data usage. And when it comes to data collection, the things to consider are, what are my inputs? What are my outputs? And be able to design it so I can accept any and all, to make it scalable, to have either local analytics or send the data up to a higher level analytics system, and to visualize that process. For data transportation, we need different types of switches. We need segmentation. We need it to be scalable. And we also want to try to induce redundancy wherever possible. For routers and data security, we need to add routers. For security, it's really important. They call it depth in security is depth in application. So at each layer, we want some form of security. It's not like we can just add one device that's the security device and it covers everything. Each time we move the data from the machine to the one level to the next level, we need to have security designed into each step of that process. And lastly, on the data usage, we as Phoenix Contact, we remain kind of ambiguous to that portion. You can use whatever you'd like. If Ignition is your thing, if AWS, whatever cloud service analytics thing works, there's lots and lots of people that do data analytics. We just consume data, help produce it, we normalize it, and we'll provide it to the higher level systems. So to kind of wrap things up, as I mentioned, as part of Digital Factory Now, we've had our own digital transformation within our company. Starting in 2019, we said, look, if we're going to get into helping other customers do digitalization, we should really walk the talk and do it ourselves. So we took our factory in Bod Piermont, which makes a lot of our electronic devices, and it became our lighthouse digitalization plant. And so we've taken many of these, the concepts that you've seen today, we've applied them to that plant, and we offer to you today a 360-degree virtual tour of that plant, in which at the end I'll have a link for you to go to, or a QR code that we can send to you down the road. But internally, now that we've been doing this for a few years, on the left, we started with these manual work instructions. Today, what you see here is basically, you hear the word digital twin. We've basically twinned all of our process. So we have the process running in real time, and we also have a twin of that process running, so that as we can look for anomalies and detect things and changes on the plant floor, we have both as a backup. And we've taken all those work instructions and we've put them into a digital format that's available and can be visualized on screens all throughout the plant and each workstation. And the result of that is we've realized about a 10% increase in efficiencies just by monitoring a few data points each. We've really collected less than all of the data in each station and PLC. We only consume about 5% of that to really form and develop the analysis we need. So it's not like we're sending all of the data out of the equipment to get the results that we need. So that tour is available, and again, I can either get this to you, I'll give you my email here at the end, and here are some resources for you. So we have a YouTube channel, and via that channel, we have a lot of different educational resources on this topic. We have a whole community set up. As I mentioned, we are very open source minded. So we make devices just like Apple makes an iPhone. The iPhone in and of itself doesn't do anything. It's the application community that develops the apps. We take that same approach to PLC and machine level control and digitalization. So you can go to the PLC Next community through GitHub. You can grab code. We want to share this. We don't want to make it proprietary. So there's a number of resources. Feel free to reach out to me personally, and I'll send you any information or put you in contact with one of our, whether it's our engineering or our sales team that are local to you. So remember, we need to collect the data, we need to transport the data, we need to secure the data, and we need to use the data. And we can help you in all of these areas through any one of these devices. So with that, I'd like to say thank you very much for your time today. And I'd like to open the floor and open my chat to any questions you may have.
And I'll jump on here, Mike. We do kind of have a hard stop. So if anybody does have any questions, feel free to just message them to Automation Alley, to Mike. And please remember, this webinar is recorded. So feel free to watch it again, to share it with your network or anybody you think this information is relevant for. Thank you so much for joining us this morning. And remember, we do have another Tech Takeover next week with Amran, where we'll be diving into practical approach to gathering meaningful and useful data. So thank you everybody that joined us this afternoon. And like I said, if you have any questions, feel free to reach out to Automation Alley or to Mike directly. And again, thank you, Phoenix Contact. This has been wonderful. So much useful information. And everybody have a good rest of your afternoon.
Thank you, Allison.